chemical equations are just the way to express a reaction as simply as possible. So, for example, if we're looking at the process of making water, hydrogen gas and oxygen gas are what we would call the reactants. So those are the substances that come together in the reaction and the substances that undergo the chemical change. The products are what is the result of that chemical change. The arrow just represents the process of the reaction. And the other word that we need to remember, well, there's really two others. Coefficients, okay, these represent how many molecules of the substance are required for the reaction to work. And then the subscripts represent how many of the atoms are in that molecule. So the subscript is the thing that we reviewed even when we were talking about naming and turning names into formulas. The coefficients really belong with what we call balancing chemical equations. So as a reminder of what that means, okay, if we're looking at this combustion example, if you're looking at it, you might notice, on this side, on the reactant side of the reaction, there's only 2 atoms of oxygen, but on this side there are 3. That's obviously not really possible. You cannot create or destroy an atom during the course of a reaction. There has to be some way for atoms to combine and change in whole numbers, and atoms all stay the same. What changes is the way that they're arranged. So for example, like this carbon atom here, okay, it's a carbon atom on the left and on the right, but its properties are different based on who it's bonded to. So on the left it's bonded to hydrogen, on the right it's bonded to oxygen, but it is still an atom of carbon. And the way that we fix this problem to represent that all of the atoms on the left and the right exist before and after the reaction is what we call balancing. To give you a better visual of this, I found this picture. So a balanced version of this same reaction shows that what we really need for this to work are 2 molecules of oxygen, because they end up divided here and here. So 2 of these are going to make water, the other 2 are going to make the oxygens on carbon dioxide. We still only needed 1 atom of carbon, but we did need to have 4 atoms of hydrogen, so again this 2 coefficient is what balanced that reaction. If you're working on balancing one yourself, the first thing that you have to do is look at how many you have. So this table kind of summarizes that before the reaction there are 4 phosphorus, there are 2 hydrogens, and there's 11 oxygen. After the reaction, with this making acid, there's 3 hydrogens, 1 phosphorus, 4 oxygens. Okay, that's obviously not possible. You can't lose phosphorus, you can't lose oxygen, you can't mysteriously create a hydrogen. So that means there has to be more than one of these molecules going on either side of the arrow. I wish that there was a rule I could tell you about what's easiest to start with, but there isn't. In general, if you're looking at this situation, okay, so oxygen is split up into 3 parts. That means it's not going to be the easiest element to start with. So you want to look at these equations when you're balancing them and pick something that is easy to start with. And if I feel like personally, in this case, the phosphorus is the easiest one. So there's 1 phosphorus on the left. The only way to represent that there are still 4 phosphorus as a product is to put a 4 in front of this molecule. So now we just changed the number of phosphorus to 4, but since it's a coefficient, it affects everything behind it. So we've just changed the number of hydrogens to 12, and we changed the number of oxygens to 16. So now our phosphorus is balanced, but we are still unbalanced with oxygen and hydrogen, but the issue has shifted to the left side of the arrow. So if we're going to fix that, okay, the only way, again, oxygen's still not that easy because it's split up into more than one place. So I'm going to balance hydrogen with a 6 here. Okay, that changes my hydrogen to 12. And now, if you look at the fact that oxygen is in more than one place, it doesn't matter if they're attached to the same molecule, it just matters if they're on the correct side of the arrow. So we have 10 oxygens here, and now we just made 6, which means we have 16, and that balanced our equation. So the thing that makes it difficult is the only thing you're allowed to add to an equation is a coefficient, which means that you end up going back and forth quite a bit. If we're solving a simple one here, oh, that is not supposed to be there. Okay, if we're solving a simple one, there are 3 chlorines on this side. There's only 1 chlorine here, so I'm going to put a 3 in front of that sodium chloride. So what that means is, at the minimum, this reaction creates 3 molecules of sodium chloride. If I've changed my number of sodiums to 3, that means I must have started with 3 in the very beginning. And now this is a balanced equation. So iron did not need anything. There's 1 on both sides. Okay, if I'm balancing a harder one, you can look at a polyatomic ion like it's a whole unit. So there's 1 phosphorus on this side, but there's 2 phosphorus here. So I'm going to put a 2 in front of this molecule to represent that there were 2 phosphorus ions involved the whole time. That changed my lithium to 6, so I put a 3 here. Okay, that changed my amount of carbonate to 3, so I need to put a 3 here. And that changed my calcium to 3, but when you go back to the other side of the arrow to fix it, there are already 3 calciums. So now this is complete. So it's a 2, 3, 3, and this is an invisible 1. Okay, a few more examples. Let's see. So again, oxygen, not a very easy one to start with because it's split up into so many places. So I'm going to start with carbon. We have 3 carbons on the left, multiply by 3 to make 3 carbons on the right. We have 8 hydrogens, so I'm going to multiply this by 4. And now carbon and hydrogen are good now. We have 3 and 8. Oxygen is still split up, so we need to check with how many are on this entire side. We have 6 here, and we have 4 here. So that means I need to make this molecule 10, so I'm going to put a 5 in front of it, and that is done. Okay, so they can get pretty tricky, but nothing, it's not extreme. I don't think you're going to have any that are, like, unsolvable. This one's just bigger numbers. So put a 12 here to balance carbon. It's the same situation as last time where oxygen probably needs to be saved for last. So 12 in front of carbon, 11 in front of hydrogen. And now we have, let's see, this is 24 plus 11. Okay, so we've got 35, which is a very awkward number. When we go back to the left side to figure out how am I going to get 35 oxygens on the left, what we need to remember is there are 11 in this molecule and 2 here. So 35 minus the 11 we already have takes us back to 24. And now that's really easy to balance. So I don't want to mess with this molecule if I don't have to, because that's going to change carbon and hydrogen. I'm going to go ahead and subtract my 11 and look at making the one that's a free molecule, the O2. I'll make that one 24 with a 12. So this balanced equation is 1, 12, 12, 11. On the AP level, you're expected to take it one step farther, where you're going to have to actually be able to write the equation out and balance it. So before I show you an example of that, I want to remind you, okay, you do need to know the 3 states of matter, which hopefully you remember, but those actually need to be incorporated into a chemical reaction. So if it says like you have solid carbon, then you're going to represent that as C with an S to show that it's solid. Okay, if you have liquid water, then it's H2O with a cursive L. If you have gaseous carbon dioxide, then you'll put a G. There is one other state of matter, which is called aqueous, okay, and that is ionic compounds dissolved in water. So, for example, sodium chloride, okay, if we dissolve it in water, it's aqueous. And in your book, chapter 3.11, has examples like this one where you have to write out what it says and make sure that you put the symbols, and then you have to balance it. So we're going to start with solid cobalt-3 oxide. Okay, that means the cobalt has a charge of 3. If you look up oxygen, it's -2. So we're going to start with CO2O3, and it's solid. Okay, it says it reacts with solid carbon and produces solid cobalt and carbon dioxide gas. Okay, so you've written it out. Now we have to balance it. We have, let's see, what would be the easiest thing? We have a situation here where we have an odd and an even number. So the easiest way to fix that is with a common multiple. So I'll put a 2 here to make 6 oxygens, put a 3 here to make 6 oxygens on the right. That made 4 cobalt, so I put a 4 here. And let's see, we have 3 carbons, so you put a 3 here. So it's 2, 3, 4, 3. Combustion reactions are all the exact same except for the CH substance. So in this case, it tells you that you have C2H6. If it's combustion, that means it's reacting with oxygen gas. and it's making carbon dioxide and water. So we're going to balance, again, oxygen, don't start with that. So we'll start with a 2. Oh, you know what? I forgot something. I forgot to type that everything was supposed to be a gas. So, excuse me. It all is supposed to be a gas. Oxygen gas, carbon dioxide gas, water vapor. And then most of the time with combustion, we're starting with some kind of carbohydrate that is a gas. So let's see. We're going to start with carbon. We need 2 carbons here. We need to make 6 hydrogens. So that's a 3. Okay. So here we have 4 oxygens. We have 3 oxygens here, so that means we have 7 altogether. That is a problem. And the problem is that this is only an even number. So the only way to get 7 out of O2 is with a 3.5, which is not appropriate because you can't have half of a molecule. And what that half represents is that all of these coefficients are only half as big as they need to be for the reaction to be balanced. So if you want to solve this the easy way, if you ever end up with a half number as a coefficient, you know that you just need to double everything. So this is going to be 2, 7, 4, 6 as a final answer. Okay, last example. We have lithium phosphate. Lithium is +1, phosphate is -3. Oh, whoops, I skipped strontium chloride. Well, whatever, it doesn't matter. Okay, so we have Li3PO4. Okay, and it says it's aqueous. Strontium is +2, chlorine's -1, so SrCl2, it's also aqueous. On the other side, we are switching the, this is a double replacement, so we're switching the metals, but the charges stay the same. So strontium is +2 on both sides. So we're going to end up with Sr3PO42, and it says this is solid, which we call a precipitate. Okay, and then lithium chloride, that's +1, -1, so LiCl is aqueous. And then to balance, we're going to go through, this is 3 lithium, so I'll put a 3 here. That made 3 chlorines, and so here I've already run into a problem. I just made 3 chlorines here, but this is 2. So that already lets me know that the 3 is not big enough. I'm probably going to have to deal with a common multiple, so I'm just going to erase that and change it to a 6, and change this to a 3. So now I made 3 strontiums. If I go over here to fix that, I realize it's already 3. Okay, I have bumped this number up to 6 lithiums, which means I need to put a 2 here. Okay, that means I now have 2 phosphates, but there's already 2 phosphates on the right. So this is now balanced with a 1 in front of strontium phosphate.